All right, we've talked about benthic organic products, but not all organisms live on the seafloor. Some of them live in the water column or up in the ocean. We call these pelagic, occurring within the water column. Um, and much of what forms in the water column, I'm not thinking about like big whales and dolphins and fish, right? I'm thinking about tiny, tiny little organisms that you might need a microscope to see, like algae, right? And these algae can be formed from a few different minerals. Regardless of what mineral it is, though, if a lot of them form and then deposit on the seafloor, we call it biogenic ooze. And I love that word, ooze. When I first learned it in undergrad, I thought my teacher was joking, but she was not. We do actually call it ooze. So biogenic ooze, it's any pelagic sediment that contains more than 30% skeletal material. So there can still be some aeolian clay, right? There can still be some terrigenous sand. But if at least 30% of the sediment is formed from biologic material, we're going to call it a biogenic ooze. And they can be made up of either calcareous ooze, which is carbonate based, or siliceous ooze, which is silica based. We're going to talk about both of those. So calcareous ooze. This is predominantly made up of algae such as coccolithophores or foraminifera. We shorten those words because both of those words are very long to just coccoliths or forams. And you can see that coccoliths are round. They're made up of these little discs. Foraminifera, they come in lots of different shapes and sizes, but a prevalent form kind of looks like popcorn. These are both, their shells, or we actually call them tests on these organisms, are made up of calcium carbonate or CaCO3, so we call them a calcareous ooze. And remember that carbonate or calcite or aragonite dissolves, right? Calcite is more stable than aragonite, but both of them do dissolve in an acidic ocean. And so there's different parts of the ocean where if these sediments deposit, they remain stable versus other parts where if they deposit, they'll just dissolve away and never to be seen again. So in the shallow ocean, where there's lots of calcium carbonate production, right? That's where you have lots of nutrients, you have lots of sunlight. That's where these organisms are growing. There's lots of calcium carbonate ions in the water column. So because there's so much carbonate there, the carbonate isn't going to dissolve, right? Because it's oversaturated there. Also, the water is going to be warmer and it's going to be under low pressure, which means that the water itself isn't going to be able to hold much carbonate. So if there's solid carbonate, solid calcite, it's going to stay solid and not dissolve into the water. However, if you go deeper, you're eventually going to pass the lysocline. The lysocline is the depth at which calcite and aragonite start to dissolve. That's because it's getting deeper. Therefore, the pressure is increasing, the temperature is decreasing. That means the water can hold more ions in solution. So those solid carbonate like shells are going to start dissolving into the water. Also, when you get that deep, there's a lot of dissolved carbon dioxide in the waters, which makes the water more acidic. So it's more likely to cause rapid dissolution. So the lysocline is where carbonate starts to dissolve. What we call the CCD or the carbonate compensation depth, that's where it will dissolve, right? It's not just going to start dissolving. It's the dissolution is faster than the precipitation at that point. So it's very, very unlikely that you're going to find any carbonate deposited lower than the carbonate compensation depth. Um, However, you can in some instances. So in this extrapolative thought, I want you to think about why we can see calcareous ooze below the CCD at a mid-ocean ridge. Think back to what we know about mid-ocean ridges, how they form, how they move. Also think about what you know about calcareous oozes, where they come from, how they deposit. Um, and look at this image and see that there is calcareous ooze or that green bricked symbol that is actually below the CCD. How is it still there? Why isn't it dissolving?